thank you very much for inviting me to be here. I enjoyed very much Professor Lee's talk, and I'm looking forward to hearing everyone else's talk, what's going on here. I particularly like the beginning slide that Professor Lee showed, where he showed that understanding the gravitational wave events then flows into the multi-messenger astrophysics, and that can then flow into the cosmology. And so even though I will mostly focus on the cosmology aspects, I will try to make ties to each of the other aspects, the gravitational wave properties, event properties, and the use of the multi-messenger detections as well. So I'm pretty much going to have a blend of theory and data interpretation. I'll start off a bit more on the theory side and end up a bit more with what the data are actually telling us so far. Okay, so it's been more than 25 years that we've discovered the universe's expansion is accelerating. And I think every day when you wake up in the morning, you should still think, even 25 years later, wow, this is just an incredible discovery, an incredible change in the way that we view the universe. So the general picture that you have is you start in a hot, dense early state. You have a rapid expansion that we call inflation in the very early universe. And then you have this long period where you have radiation, matter, seeds from inflation become eventually galaxies, clusters of galaxies, black holes, and so forth. But then we really hadn't expected a few decades ago that there would be this second period of rapid expansion, this cosmic acceleration. So this turnaround is just not at all part of the standard model that you get from particle physics that you learn about in your particle physics classes. Well, before you ever took a particle physics class, when you were a toddler learning to walk, you learned about a fundamental force of nature. You learned about gravity. You kept falling over. And you learned gravity is always attractive. You always fell to the floor. You never fell up to the ceiling. And even when you do take physics and you do your studies, you still learn gravity is always attractive. And so that should be slowing down the cosmic expansion. The matter, the energy in the universe should be pulling things back together. They should not be flying apart from each other faster and faster. And so that's why this is really extraordinary. And I've pulled out a couple of quotes from soon after the discovery of dark energy is the name that we give to cosmic acceleration, from some physicists who really say this is like the most profound gap in our understanding, just not understanding why is the universe accelerating currently. Let me tie it a little bit more to the data, to what we actually observe. So if we look at the expansion of the universe, if we are measuring distances out in the universe, whether it's through supernova explosions, baryon acoustic oscillations, gravitational wave sirens, and so forth, we measure distances. That means we're measuring how fast the universe is expanding as a function of that redshift. And so, as expected, the expansion rate slows down. Gravity is attractive. You just keep pulling things together. But observationally, we see that no, we have this turnaround. The expansion rate more recently is starting to speed up. So that was not expected a few decades ago. And often when we do fundamental physics, when you go to CERN, when you do laboratory experiments, you're really trying to do a part in a million, a part in a billion detection. I'm looking for this really strange, really rare event, or I'm looking for this effect that's off from Newtonian or off from general relativity by a part in 10 to the 10th. And that's not what cosmic acceleration is. Cosmic acceleration is an order 1 change in our understanding of the universe. And that is why it is just so amazing. So that's when we measure distances. The other thing that we're very good at measuring in the universe is that we can measure how do things cluster together. So the spacing of galaxies, we make a 3-dimensional map. We look at the spacing of galaxies, how things cluster together, how they move, their velocities, and their distances relative to each other. And so if we look at that growth of clustering, again, gravity is attractive. There should be more and more clustering as the universe goes on. If we look at how that goes, We can predict it analytically, really, in a matter-dominated universe when gravity is just purely attractive. And we can say, okay, we're going to call that 1. We're going to normalize that growth rate to 1. And then we can measure the growth rate. And what we find is it does not stay 1, but it starts dropping off. The growth rate is slowing down. It's being suppressed. And that is another effect of this cosmic acceleration. The galaxies want to cluster together in their gravity. Cosmic acceleration is pulling them apart. And eventually, so we live here today at log of a is 0, that is, the scale factor is 1 today. We're sort of in the middle, but as we go into the future, growth will simply completely shut off. And so that is, again, cosmic acceleration has this amazing effect on both distances and growth in the universe. So the leading idea that one would have for how you get this acceleration is Einstein's cosmological constant, called lambda. So you'll often see people talking about lambda. And this is just a uniform energy density in space and time. We have no idea why it's really there, but that's the simplest thing you can do. We just write down one number. And again, Einstein came up with this a long time ago, so we figured that's a good first guess. But there is no good theory. And the little star says good means that, well, someone other than the author of the paper actually believes the explanation for it. So if you want to go beyond just this one number that somehow got set in the very, very early universe, then you put some dynamics. So this dark energy, this anti-gravitational force, is being dynamical. So both its pressure and its energy density are time dependent. So in the energy momentum tensor, you know it's a 4x4 tensor. You've got a pressure piece and you've got an energy density piece to it. And it's very convenient to talk about the ratio of the pressure to the energy density. And we give the symbol W to that. We call that the equation of state ratio. So throughout this talk, or most any cosmology talk that you see, there'll be lots of W's around. So just think of it as the pressure to energy density ratio. One way to go beyond this very simple level field, cosmological constant, is you can have a scalar field that rolls in its potential. Or you can change the theory of gravity. You can say gravity is not always attractive. Both of those can be basically treated through this pressure and energy density, through the effective energy momentum tensor that you have. Okay? And so I will be talking about W, and that doesn't mean that I think it's a scalar field. It doesn't mean that I think it's a modification of gravity. It can be either one, and you can still treat them the same way. So the problem that some people have is they grew up with lambda, they grew up with the cosmological constant, and they're very reluctant to look at anything else. And they say anything else must be a horrible thing. Who knows what it's going to do, this dark energy, is if you're giving it some dynamics. Maybe it's like a roller coaster. You're just going all over the place. You can never tell how it's moving, what effect that will have on distances and growth. So what I want to emphasize is that's not quite true, that we actually understand a lot of the physics of the general characteristics that the dark energy should have. So the phrase that I like to say, which is a bit of a jokey phrase, is dark energy does not exist in a vacuum. It's a bit of a joke because the cosmological constant is the vacuum energy. And so you would say the dark energy is the vacuum. But what I mean here by dark energy does not exist in a vacuum is that there's a lot of other energy density in the universe. There's the matter and the radiation. And that has existed for billions of years, many, many E-folds of expansion. And that is going to govern how does the dark energy evolve as well. Because the equations of motion, the Friedmann equations, depend on all of the energy densities together. We know that there must have been many, many E-folds of radiation and matter. We look at the cosmic microwave background, a signature of the hot, early, dense universe. We have Big Bang nucleosynthesis. We have the growth of galaxies early on and so forth. We know that matter and radiation must have dominated early on. And so if dark energy lives in that universe for billions and billions of years, its evolution will depend on the expansion governed by the radiation and the matter. Today, the expansion is governed by whatever the dark energy is. But again, you had this long period where the radiation and matter governed, and so that makes things very simple. You basically have only two forces. You have a Hubble friction from the expansion rate. So a field is trying to move along, but space is stretching underneath it. It's expanding underneath it. And that gives you a friction term. And then you have a driving term from the steepness of this scalar field potential. So if you like, you can look at it as, well, if there's a lot of friction on the track, if the wheels on the roller coaster are not very good, then the roller coaster is not going to move very quickly along this. Or you can say, well, there's a really steep section and it doesn't, it's just going to fall. It's really going to move very quickly. And those are really the only two forces that enter into the problem. And so that gives you a pretty simple relationship. One or another of those forces is likely to dominate. So if the friction force dominates, then again, you're sort of frozen into place and you look like a cosmological constant. But as the universe expands more and more, then you are diluting the radiation and the matter. You're reducing that friction force, and the field can now start to roll. That roller coaster can now get over the top and start to go down. And so that case, where the friction dominates early on, we will call the thawing case, because it was frozen and now it's starting to be released to move. And it will move away from a cosmological constant. Or we can be on the very steep part of the potential. The field is rolling, but you can't stay steep forever. You've got to level out unless you're going to go through zero, which is a completely different way. So it's got to become more shallow, and then the friction will dominate later. And so then you start off evolving, but then you slow down as you get toward the minimum, and it freezes. So that's called a freezing field. And that's moving toward a cosmological constant behavior. And so we really do expect that the cosmic acceleration should have this, one of these two behaviors. From just the very basic physics that the dark energy evolved in this universe that had many, many expansion doublings or E-folds in matter and radiation domination. So as I said, we like to work with this ratio, the equation of state ratio W. One of the reasons we like to do that is because it determines the expansion rate. So of every component, you look at the pressure to density ratio and the density, and you will get the Hubble expansion rate. Okay. And one of the reasons we like to deal with W rather than a field itself is because if we're dealing with modified gravity, there isn't necessarily a physical field, but you can still phrase it in terms of this equation of state. And so this will hold even if what we've done is we've changed general relativity. So again, we have one of two situations. Friction dominates or steepness dominates. You either are thawing or you're freezing. And so we expect the evolution of the dark energy to lie in two fairly narrow regions in this phase space, if you like, the equation of state and its time variation. And how should it go? So this is a plot of the phase space. Here's the W, here's the W prime, the time variation. And we get these blue freezing and thawing regions, fairly narrow regions within that. And for many years we thought, okay, that's all we have to do now is collect enough data that we will figure out which of the regions it lives in, how far from the cosmological constant, this -1, 0 point, does it live? So does it lie up here? Does it lie down there? Is it far out? Is it close in? And we thought that was all there was to do it. As I'll get to in a couple of slides, we've been really surprised this year, basically in April of this year, when the dark energy spectroscopic experiment came out, and you plot where its data will lie in this plane, and it does not lie in one of the two expected blue regions. And so the question then becomes, well, what is outside those two regions where we thought things were just so simple that either friction dominates or steepness of the potential dominates? The first thing you can think of is, well, maybe they're balanced somehow. So if you were to balance those two forces, you would lie in this middle region. you're balancing, so again, think of the roller coaster, you're balancing between the friction and you're balancing between the steepness of the potential in such a way that the acceleration of the field is zero. One force balances the other, not just at a single moment, but over a long period. So that's a sort of fine tuning. So on your roller coaster ride, that means you're just moving along the roller coaster at a constant velocity, no acceleration. It's a pretty boring ride. And it's not something you would expect physics to just come up with automatically to fine tune things that way. So that's why we thought things should not lie in this middle region, which corresponds to a constant W. What about this left half of the plane where W is more negative than -1? This means that the pressure is not only negative, but it's more negative than the energy density. This does very strange things to the energy momentum tensor, and it does something that's called violating the null energy condition. It's not something that you would tend to write down in your physics. It would be something that's definitely a surprise. And it was such a strange thing that people gave it the name of the phantom region. Okay, it's this sort of other type of physics that we just would not expect to have. But maybe, we have to leave our minds open. Maybe it lies there. And then we have this high region and this low region. The low region is where you actually roll uphill on your roller coaster. Okay, you put a ball on top of a track, it starts to roll down, nope, it decides to roll back up the track. Again, it's not the sort of physics that we thought there should be, although we knew there were ways to do it. You basically, so tachyons can do it, something that moves faster than the speed of light. But even besides that, you're basically flipping the sign. Oh, sorry, I'm doing the low region. You have to change the kinetic structure. You have to do something very odd to it. So we sort of knew ways to do it, but you would really have to do something extra. And then there's this high region where you violate early radiation matter domination. So that's the one we thought definitely is not going to be the case. We know Big Bang nucleus synthesis, CMB, we know that there was early matter and radiation domination. So spoiler, the data ended up there. So I'm going to explain how that ends up being not a ridiculous thing to happen, that you have to look very carefully at the way the words are, and that there is a way to do the violation without actually changing the early universe history. But I'll get to that in a few slides. So let me move into the data a bit, since I've been talking about that. It's really an incredible endeavor going out and mapping these millions of galaxies, not only the positions on the sky, but the distances. So we heard in Professor Lee's talk how difficult it is to find these objects, to map them to further and further distances, and to actually measure the distances precisely. And so a special experiment called the Dark Energy Spectroscopic Instrument was created. It's actually 10 spectrographs together with 5,000 fibers that are robotically positioned, rearranged every hour basically to look at new galaxies. It's really incredible engineering going on. So this is the Mail Observatory. It's a 4-meter telescope in Arizona in the United States. And this is an artist's impression of mapping out these patterns of galaxies, this cosmic web of galaxies, to further and further redshifts. And then eventually you're at high enough redshifts, you get to the cosmic microwave background, which you do not see with the optical telescopes. Those are different experiments. Beyond the technology that we have today, you really want to remember the people who've gone before and how much work they had to do to get to where we are today. So this is the number of redshifts that have been measured of cosmological objects as a function of history. So back in the 1980s, we were at about 1,000. The best maps then, the revolutionary maps called the CFA map, the first really big one, was about 1,000 redshifts. And you can see that now we're all the way up here at DESI. So now we're measuring tens of millions of redshifts. And so that's really an incredible amount of progress. And then there are certain people who like to just extrapolate this and figure out when are we going to observe every galaxy in the universe? And the answer is around 2060 or so. You get to all of them. People haven't quite planned to 2060, but they have planned to about 2040 or so. So again, it's the technology advances and it's the teamwork of getting people to do these big projects, to have the vision and then to do the engineering, the detectors and so forth. So as I say, DESI is such a dramatic step forward. It has already mapped about 10 times more galaxy redshifts than all previous surveys. And so that is pretty amazing. So it released its one-year data in April of this year, looking at distances through something called the baryon acoustic oscillations, which I won't go into. So if you remember from the previous diagram, we had a narrow region here and here. I've switched to a parameter which actually has a sign change from what I saw before. So the high region is now down low. Here's the thawing region, the one where the friction dominates. And you can see it's a pretty narrow region. And we're definitely not really lying in that region. We're definitely lying below it. So that's what used to be the high region. But because of the sign flip, it's now a much lower region. Don't worry about the three different contours. They're all basically agreeing that you're not really, your best fit is not at the cosmological constant, and it's not in the thawing region. It's in this, what was the high region, the region that seemed to violate matter and radiation domination. So I do want to give a bit of a caution on the statistical significance. It was very, very carefully phrased in the papers from DESI. That said a tantalizing suggestion of deviations from lambda. So enough that you might want to write some papers on it, but not enough that you would maybe give up on everything else. So it's of order 2, 3. Some people will go up to 4 sigma deviation from lambda. It's the year 1 results. DESI is a 5-year project. The year 3 results will be coming out next year on the distances. Year 5, a couple years after that. So we're going to learn a lot more, as I'll talk about here. But let's take it at face value. Let's suppose that the best fit value really was where I just showed it as off from lambda and off from thawing, that it's somewhere down here. What would that mean? So what that would mean is at high redshift, above redshifts of 1, you'd have to be in that phantom regime. W much more negative than -1, violating the null energy condition. But then you have to evolve very, very quickly, faster than Hubble friction seemingly allows, seemingly violating the evolution you would expect in matter and radiation domination. You then have to cross the W of -1 line, so you basically zip through the cosmological constant value, and then you evolve to less negative value of W today. So the interesting thing is, in the literature in the 2000s, before the observations, there were papers explaining how you could do each piece. So those zones of avoidance that I showed, we know how to basically do each piece of that. But we did not expect any model to do multiple of these, let alone all 4 together. So this was really quite a surprise. So let me talk a little bit about how we might encompass that surprise and come up with an idea of what's going on. So this, what is this doing? So there were some slides that were hidden, and they're not, it seems not to be hiding them. I'll talk about them very quickly anyway, even though I think they were hidden. So one thing you can do is ask, well, it appears to be crossing this W equals -1 line, but is it really? Could you simply be apparently crossing -1 because of the particular way that you did the phase space, what's called this W0 WA parameterization? And the answer is yes and no. If it's a mild crossing of -1, so the orange and the green line, the orange line never crosses -1. It simply goes to -1, whereas the green one does. They will both have about the same W0 WA in that thawing region that I showed. But one crosses -1, one does not. And so what you can say is, oh, we never actually violated anything. If the data had lain up here, we could say, oh, we never actually violated the null energy condition. However, what we actually lie in the blue and the red values of W naught WA, which have a much sharper crossing of -1. And then you can ask the red line, which again never crosses -1, it only goes to it. And the blue line, which again has the same W naught WA, but really does cross it, can we distinguish between those? And so our collaborators at COSI have done that calculation, and they find that the data prefers the blue line, a true crossing, by about 3 sigma. And so this is very significant. It's saying what the data is telling you is a real effect. You really are going into this phantom region. So what we're really doing is we're not trying to understand the particular value of W naught WA, a particular value of the equation of state. We're really testing the framework of asking, how can you get into this region where we thought physics would not allow you to go? How can you be in one of these zones of avoidance? So what you're doing is you're testing the physics of the equations of motion, of the scalar field. So the scalar field equation of motion, the dynamics, it's called the Klein-Gordon equation. It's a simple second-order equation. It's like a wave equation, basically. A driven equation with some friction as well. It's basically a roller coaster, the same equation you write down for a roller coaster motion. So let's look at the other period of cosmic acceleration back in the very early universe. When we had inflation, we started off, when we tried to measure inflation, with measuring the dynamics. We measured the tilt of the scalar power spectrum, what's called NS, and we measured the proportion of primordial gravitational waves. And there was a consistency relation between those. We haven't actually detected those primordial gravitational waves yet. But then you can also go beyond the dynamics, and you can look at other features, in particular of the sort of clustering of the primordial perturbations, called non-Gaussianity. So we're going to do something very similar for dark energy now. Beyond W naught W prime, beyond the dynamics, we're going to look at not the non-Gaussianity, but what I'll call the non-Klein-Gordonness. What is going on in the dynamics that is so strange? So in inflation, you have 3 basic ways of getting this non-Gaussianity, this extra physics besides the dynamics. You can either change the kinetic structure, which, if you remember the zones of avoidance I mentioned, you can have multiple fields. So here's an inflation field where one field would be very happily just roll straight along this axis, but there's another field, there's another dimension that can push it now off into these other minima. And so maybe dark energy has multiple fields. The other way you can do it with inflation is changing the initial conditions. You change the structure of the vacuum, what's called the Bunch-Davies vacuum for inflation. For dark energy, you can either do it through negative potentials or a phase transition in the dark energy process. We can also look not for primordial gravitational waves, but for any signatures of gravity beyond general relativity. So we have a consistency test. What we learned from growth of structure, is that consistent with expansion distances? We can look at the effects of gravity on matter and light beyond what we expect in general relativity. So the growth of matter and the bending of light by gravity, gravitational lensing. And we can look at what's called gravitational friction on the way gravitational waves propagate. So in general relativity, as Professor Lee said, we can measure distances, we can measure waveforms, and so forth in general relativity. If there's gravity beyond that, then you're going to change the waveform if you're changing the gravity at the source. But if you're changing gravity in the intervening universe, you change the propagation. So you can think of this, if you like, as a change in Newton's constant or change in the Planck mass with time. And so that is another way that we can try to get a handle on things beyond just the simple dynamics. So the answer is going to turn out to be something very similar to a phase transition for the dark energy. So let me go into a little bit more detail. Oh, no, that's right. Here I won't go into detail. I'll just say one of the ways that you can get these 4 different things is if you change the structure of the vacuum, you basically give it a phase transition, and that solves that paradox of, we said dark energy should be evolving for many, many E-folds in a matter and radiation dominated universe. We don't want to violate matter and radiation domination, so instead we violate the first part. It was not evolving for many E-folds. It suddenly appeared within the last E-fold. And that's the way you can preserve matter and radiation domination and yet still get an answer that the data seem to indicate. We don't know that that's the case, but that's a possibility that people are looking at, some sort of a phase transition. And the Cossey group, Armand's group, has done a number of papers reconstructing in a model-independent way for the data what the behavior of the dark energy is, and it does look like phase transition is one possibility for that. The physics of how you do the phase transition, you of course still need to figure out the fundamental physics of it, but we get some phenomenology. So now let me switch a little bit from the dark energy part to interpreting the dark energy as a gravity and ask, well, how do we get a handle on that? So we have that consistency test of growth versus expansion. So we can do galaxy surveys and get the growth of structure and get distances through the baryon acoustic oscillation, distances through the supernovae, and again, distances and growth of structure through the cosmic microwave background. And we can do that test of consistency. So that's been done with previous surveys. It is currently being done with DESI, and again, within the next several months, you should hear some initial results. The gravitational effects on matter and light, so this is gravitational lensing, weak and strong lensing, and the velocity imparted to the galaxies, peculiar velocities they're called. The gravitational friction on gravitational waves are the strain distances, or the distances you measure through measuring the strain in your detector from gravitational wave events. Are those equivalent to the photon luminosity or angular distances? So this is where the multi-messenger aspect comes in so importantly. You measure the gravitational wave distance. If you see an optical counterpart, you measure its distance, and you ask, what is their consistency between those, either for an individual event or statistically. So again, you have to find the electromagnetic transients, and that's why I'm so interested in hearing Professor Eames talk this afternoon, how to find them, how to localize them, and then you also have to measure both the distances and the redshifts for them. So it's very much a wide open field, a frontier that is a very exciting way to go for the future. So let's think about what gravitational wave surveys would look like in the same way that we looked at how galaxy surveys evolved since the 1980s. So rather than talking about here's an event, you have a list of events, start thinking about a map on the sky of events that you have. So we can get accurate distances from gravitational wave events. And of course, you need those optical transients then. As we've heard, there are ways of doing it with dark sirens. I see a lot of issues that need to be overcome with that. I think the optical transient way, we've gotten pretty good at detecting optical transients, supernovae. You have the Rubin Observatory coming up. You have the arrays of telescopes like 7DT coming up. I think, to me, that's a very good path forward to look at. We will be able to detect gravitational waves to further and further distances, eventually beyond what galaxy surveys can reach. And again, they also test gravity very directly. They test general relativity, and they test this gravitational friction as the waves propagate to the Earth. So imagine a time when, instead of a galaxy map that we have, the sort of map that we have from DESI of the locations of all the galaxies mapping out the cosmic web, suppose we're now going to map out the black hole web, if you like, in gravitational waves. So it's a really exciting prospect that we have for the future. And just as we started off very modestly with hundreds to thousands of events, and now we're talking about tens of millions of events, again, given enough time, we're going to reach that for gravitational waves as well. We're really going to map out the universe where you don't worry about dust in the way, you don't worry about all these optical problems that you have. Gravitational waves, they just go through anything. So you really are getting a very clear picture of the universe. So in the last part, let me talk a little bit about what we expect within the next year. So we're not going to get to this sort of a picture in gravitational waves in the next year, but let me talk about what we will get in the next year. We're going to have new results in large-scale structure. As I say, the 3-year DESI results on distances will come out next March. We will get 1-year results on growth of clustering next month. We will have new cosmic microwave background results, in particular from South Pole Telescope within the next couple of months. And supernova distances, we will get many more. So let me run through each of those very quickly. So I've already basically read this slide on DESI. You're measuring the growth of structure, the growth rate through redshift space distortions. We already have 3 years of data. We're working toward the full 5 years of data. So the 3-year data will be released in March. There's space satellites from Europe. The Euclid Dark Energy Satellite will have what it's called its quick release, its Q1 release in March as well. It will cover only 50 square degrees, so it's not going to be great for cosmology, but it will give you a promise of what you will get from Euclid when Euclid does its 14,000 square degrees, the same amount as DESI, but a bit deeper. In the cosmic microwave background, as I said, the South Pole Telescope will release its results, and the Simons Observatory, the next generation, is already on the sky in Chile. So they started operating in April of this year, and they're going to grow more. In supernovae, the Zwicky Transient Factory has released properties of about 2,500 type 1a supernovae in the local universe. They have not released their Hubble diagram yet. That will take a little bit longer. But this is very important because all of the supernova compilations, they've depended on the same sample pretty much of local supernova, of low redshift supernovae, which date back 10, 20, 30 years. So having a uniform, higher technology sample will be very important when we get that out. And of course, this is many more. Right now, people use about 100 local supernovae, and now we're going to get 2,500. There's another survey in Chile, La Cia Schmidt Southern Survey, which is on the sky, a high cadence survey. And it'll pick up some lens supernova, which, as we heard in Professor Lee's talk, will be extremely interesting. I think we'll hear in Professor Eames' talk as well. There's results coming from Subaru, from Hubble Space Telescope, and from James Webb Space Telescope as well on supernovae. The analysis end of things is extremely important as well. That's something that, again, I think the Costi group and the group here are very strong in, doing this statistical analysis in a more model-independent way. You want to really check your results. DESI did a blind analysis. So they weren't trying to get to the cosmological constant. They weren't trying to get to any particular result. They just said, where is the data taking us? We're going to do all of the tests we can till we have a lot of confidence, and then we will unblind and see where did we end up. So that's very important. Null tests are very common in CMB analysis, where you do cuts on your data. For example, did this set of instruments detect the same thing as this set of instruments? Did I detect the same thing on when the moon was bright as when the moon was down? All of that sort of thing. So selection effects are extremely important, and they do give you systematics. So we heard for gravitational wave sirens, for example, that inclination is something of the source system, is something that can affect your precision very much on your distances. But is there a systematic effect as well? For example, if it's easier to detect sources with certain inclinations than with others, then you will start to potentially get a bias unless you correct for that. So any survey always make certain selection effects, even if you don't think of them. You don't stare straight at bright stars to find a distant galaxy, because you'll never see the galaxy behind a bright star. For gravitational waves, that's not as bad, although certain types of gravitational wave experiments have noise from signals. So for example, if you're looking for a primordial background, high redshift background, and you have all these white dwarf binaries in spiraling, then that's a noise that you have to subtract out accurately enough. The technology, you can't observe things arbitrarily close together. For example, you can't move your robotic fibers right on top of each other. So here's an example of what I think is a good way of an experiment actually doing its analysis and putting the systematics very much in the forefront. So this is for supernova distances. This is what the Union 3 collaboration did, where I talked about all of these null tests, all of these cuts. So here they chose a dozen different cuts that you would do and ask, what does the uncertainty, what does the systematics look like as a function of redshift? So each of these dots is a supernova sample. And 1% distance uncertainty is 22 on these scales. So you can see peculiar velocities tell you I can't use the data below redshift of 0.03 unless you do a correction, and then you have to make sure your correction is good enough. But then things like the model calibration, the instrument passbands, and so forth, they go through everything else. Those are all pretty much below 22 until you get to the highest redshifts. And there you start to worry a lot more about your systematics. But things like the dust, the Milky Way, and so on and so forth, those are not things that you worry about if you're at the 1% level. So every experiment should put up their plots like that and say, okay, these are all the systematics we could think about, and this is where they would come in and what we've done to correct for them. Consistency between the data sets. DESI did their analysis using DESI and then throwing away half of the DESI points and using instead the older Sloan points. And they found the consistency was there, that it was a robust result. Supernova, there are several different data sets. They pretty much agree. There are shifts between them, and we would like to understand fully. So the way they do their analyses are different. Many of the supernova are actually in common between them, but again, you want to understand your data. You can use different ways of measuring distances, baryon acoustic oscillations, supernovae. Hopefully we'll be able to put gravitational waves into that. And we look for consistency one through the other. And again, there's been this long series of papers from the COSI group about exactly how you should do that. Strong gravitational lensing is another way that you can do this. Gravitational wave distances are another way you can do this. You really want to test everything versus everything else. So to sum up, cosmic acceleration, just wake up every morning and say, wow, what a field to work in. This is just so exciting. We actually do understand a lot about the basic principles behind dark energy, but there are always surprises. What we're really doing is not fitting parameters. What we're really doing is we're testing the framework of the physics. We're trying to understand what are the basic physical principles. The type of things that we do for inflation, we are now starting to do for dark energy. We're looking for the gravitational waves. We're looking for these changes in the dynamics and so forth. And so the combination of things that you want, I think, are the combination of things that this Center for Gravitational Wave Universe here is doing. They have people thinking about the basics, waveforms, cosmological models, and so forth. People who are going out and getting new data, including from multi-messenger, and people who are thinking about how do you interpret and robustly analyze the data. So it's a very exciting field, and I'm really interested in hearing all of the other talks today and tomorrow as well. Thank you.